Hi, everyone, and welcome to our lesson today on working with 5.4, graphing and converting logarithmic functions. So we're going to start off with a little bit of a recap of our exponential properties from yesterday. We have properties of working with our exponential growth and decay. We did a Desmos the other day. So if we take a look at this one, we have the definition of an exponential function f of x to the a to the x, where a is not equal to 0 or greater than 0 and cannot equal 1. So we have one on our left here. It's exponential growth, where a is greater than 1, and exponential decay is when a is between 0 and 1, but not equal to either. So the domain for these both are going to be all real numbers between negative infinity and infinity. And then the range is going to be, it has a horizontal asymptote, but it's going to be where we're above 0 to infinity. Okay, so those are our pieces. So our horizontal asymptote is going to be 0. So both of these will never cross the x-axis in their non-transformed form. So they have y equals 0 as their horizontal asymptote. They both have a common y-intercept right here. There are no x-intercepts, but there's a y-intercept, and the y-intercept is over 0 up 1. Okay, and so those are some of the things we explored. There are a couple other things that are not maybe as detail important, but they are things that students will observe. What else do they have in common? They are only going to be one or the other, either increasing or decreasing. Okay, so it can either be one or the other. It's not going to change. It's going to be either fully, this one on the left is always going up, and the one on the right is always decreasing and going down for exponential decay. Another thing is when you graph them in their untransformed form, they're in quadrant 2 and quadrant 1, and then quadrant 2 is where the graph completely lies. Okay, and then another thing is that I already kind of mentioned is there's no x-intercepts with either of those. All right, so that's how the graphs look for our exponential functions. We're going to be switching over to logarithmic functions. So logarithmic functions are inverses of exponential functions. So all the properties are going to switch when we go to graphing them, and that can get a little tricky on our mind. So let's go ahead and move forward into log functions as we go forward. Okay, so the definition of a logarithmic function with base a, where a is greater than 0 and a is not equal to 1, is denoted by the function y equals log base a of x, which reads, as I said, y equals logarithm with base a of x, and is defined by, and this one in the blue box is really important and important to write down, y equals log base a of x, if and only if x equals a to the y. Okay, so they're inversely related. So in order for the logarithmic function to work, this equation has to be reversible or rewritten as x to the a to the y. So that is something that we have worked on in the past, and we're going to explore the graphs a lot more this year. The domain of the logarithmic function is going to be log base a of x is where x is greater than 0. The position right here can never go negative, and that's partly because up here in their functions of exponential, we have a horizontal asymptote. The range is going to be greater than 0 for both of these. So since you can never have outputs that are less than 0, we can never have inputs that are less than 0 or equal to 0 for a logarithmic function. So we're going to set up our domains in that sense with that as well. Okay, all right, let's go ahead and do a little bit of ones that should be familiar from last year, which is converting. So the first one is 3 squared equals 9, which is a true statement. We want to convert it to logarithmic form. Okay, so we have our base of 3. So it's going to be log 3 of 9 equals 2. So we have our base. Sometimes people will kind of draw some arrows and kind of work with some of those pieces to kind of get it flipped around. But this is definitely not our first time, hopefully, converting from log to exponent, or from exponential to log form with that. But since logs are used to find unknown exponents, they will equal the exponent, which in this case is 2. They'll end up equaling that exponent. Okay, all right, part B, jumping into some familiar territory, hopefully with an e. So e to the x equals 11. That's our base. That's the exponential naturally occurring e value. It's irrational, does not terminate or repeat. It's approximately 2.718, and we'll look at it a little bit more. But it is a number over 1. When we raise it to the x, it is going to look similar to exponential growth. So that's going to be our base. So it's going to be written as log base e of 11 equals x. And since log base E is a naturally occurring piece, it has been rewritten, and it comes from a Greek base word or Latin base word of naturalist logarithmics, logarithmus. And so what happens is we change it to ln of 11 equals x, and that's coming from some Greek and Latin backgrounds of, let me try it one more time, logarithmicis naturalogus. So that's why it looks backwards, even though we pronounce it natural log, it's pronounced the flip-flop. That's why it's ln of 11. All right, so converting from logarithmic form to exponential form. So here is where we can work with some of our arrows. So 2 is our base. So it's going to be our base of our log form raised to the exponent 15 equals x. And we could solve that. We would definitely be calculator friendly here. 2 to the 15 is a fairly large number, and the output would be x. In part D, again, natural log can be rewritten as log base E of 4 equals x. And then we could convert that form. Okay, so to do that, we would then take our base, raise it to the unknown exponent, equals 4. And so that's the converted form of e to the x equals 4. Okay, and we'll have some practice on that tonight in case you are a little rusty on it. But those are some converting forms, again, up here in the salmon colored, log base a of x, if and only if x to the equals a to the y. So we had to be able to convert, and we have a domain that we're going to be worrying about as well. All right, graphing of logarithmic functions. So weirdly, though, I'm going to start off with how do we graph 2 to the x with this exponential, but we know that logarithms and exponential exponential functions, I should say, are inverses of each other. So how does that affect the graph? So if we take a look at this, we're going to go ahead and graph. I'm going to purposely pick 2 colors, and I do encourage you maybe to pick 2 colors for your notes tonight. We're going to graph 2 to the x and then its inverse, which will be the logarithmic function. So to do that, it helps to pick whatever makes the exponent. So if we have 2 to the x right here, that exponent is just x. So usually in the center of the t-chart, we want to make that exponent like b to the 0. So in this case, if I just plug 0 in, I get an exponent of 0. That's a nice starting point. That's called a pivot point. And we can move in either direction from there. So 2 to the 0 is going to just be 1. So at over 0, we're up at 1. We talked about at the top of these notes that they typically, without transformations, will start at the y-intercept. They all have, without transformations, a y-intercept of 0, 1. And then we can go to the left a little bit and then to the right a little bit with those t-charts. So it does help to start with when your base is raised to the 0 and then go a few points in each direction. So if I plug in, let's say 2 to the first, I get 2, and 2 squared, I get 4. So we're going to go ahead and plot that over 1 up 2, and then over 2 up 4, something like that. And then we plug in negative exponents. That's where we're going to get some fractions here. 2 to the negative 1 is going to be 1/2, and then 2 to the negative 2 is the same as 1 over 2 squared. So this is going to become 2 to the negative 2, which is 1 over 2 squared, which is going to be 1/4. So we're going to go ahead and plot that. At negative 1, I'm at 1/2. And at negative 2, I'm at 1/4. And it's going to keep getting tinier and tinier, but it's never going to cross that x-axis. So let me see if I can get that graph a little bit better. Okay, so we're going to go ahead and sketch the exponential growth function. All right, it should look something like that. And it grows very quickly as you move to the right. Okay, but it will never cross the x-axis without being transformed. So like that. All right, that's about as good as I think I can get it for now. And then what we're going to do is we're going to explore the inverse. So since we started off with our chapter inverse properties, let me switch to a different color. Let's go ahead and make one that's pretty different looking but easy to read. So we'll go with green. All right, the inverse, what we learned back in our first unit is that we can switch the ordered pairs. But actually, before we jump into that, let's go ahead and fill in some of our domain and range of our original function f of x. So the domain is going to be, I can plug in any number I want for x, and I will get from negative infinity to infinity. My range, though, will never give me 0. So even if I plugged in like an integer, a negative integer of like, let's say, negative 10. Well, that's going to be 2 to the negative 10, which is 1 over 2 to the 10th. Well, that denominator is growing without bound, and so it's going to cause it to get very, very close to 0 without equaling 0. So it's going to be 0 to infinity is that. So we have a horizontal asymptote at 0 with that. And then the asymptote is y equals 0, so it's a horizontal asymptote. Okay, that's all for our exponential function. So now with our inverse function, everything's going to kind of flip-flop. So it definitely takes a lot of brain power to keep it all organized in your mind. So we're going to go ahead and take these ordered pairs that we found with f of x and flip-flop them. So it's going to become 1/4 and -2, 1/2 and -1, 1 and 0, 2 and 1, and 4 and 2. All right, so we're going to go ahead and plot those. And what's going to happen, so at first 0, 1, so the logarithmic function, instead of crossing at 0, 1, crosses at 1, 0. And then at 1/4 over, we're down at -2, so maybe right about there. And then we're at 1/2. And then at 2 over, I'm up at 1. And at 4 over, I am up at 2. So logarithmic functions graph very slowly. Let's see if I can draw this correctly here. And it will not cross the y-axis. Y-axis. It will have a vertical asymptote instead. So I'm apologizing now. I'm going to struggle with graphing. Let me start here. See if I can come down this way. Hopefully you'll have a better success on sketching it on your paper. Okay, and so our graph then, it's tricky. Our graph will come down and it will, and I encourage you to graph this on your calculator, and we'll get one out in a little while, because it's going, there we go, much better. It's going to look deceivingly like it's going to stop maybe at like -1, 1, and it doesn't. So the inverse equation is going to be a little trickier to work with on that. So that is going to be, I'm going to mark it. We haven't found the equation yet, but that's f inverse. Okay. So that is our function inverse, and then I'll go ahead and mark my other graph real quick while we're up here as f of x. So we have our function and we have our function inverse. So how do we find an inverse? Well, back in our first unit, one of the things we did is down here, there's 3 steps typically. For this one, it helps to change f of x to y. Not everyone will have to do that as a full step, but they'll switch it. And then we're going to switch x and y and solve backwards for y. So I'm going to go ahead and stay in green since that's my inverse function. So our function is y equals 2 to the x. So I'm switching it from f of x equals to y equals. I'm going to switch my x and y's and make it x equals 2 to the y. And so what we're going to have to use is our converting form from logarithmic to exponential right up here from the top. That if we have logarithmic, y equals log base a of x, if and only if x equals a to the y. So we can switch around those pieces. So that's what we're going to go ahead and do, is convert forms. So that our base is 2. So this is going to become log base 2 of x equals y. Now that y is temporarily placed in there, but it is actually f inverse of x. So I'm going to rewrite that is log base 2 of x. So that's going to be our equation that we have graphed in green. Okay, so I'm going to write that up here as log base 2 of x. So logarithmic bases, notice that 2 to the x and log base 2 are going to have that same base when we are inverses. So the domain then in green is going to take the properties that we have of our exponential function and switch them around. So you can kind of, the better you graph 2 to the x, the easier it will be to identify domain, range, and asymptotes for the logarithmic. So if we look at the green function over here, it's going to get very, very close to the y-axis without crossing it. And the range from the exponential function is going to switch. So the domain is going to be from 0 to infinity. And very, very slowly, though, the graph will grow on that. So it does really almost look like the green graph, my logarithmic graph, could have a horizontal asymptote, and it doesn't. It is going to have a domain of, a range of all real numbers from -infinity to infinity. And it has a vertical asymptote at x equals 0. So if my exponential function has a horizontal asymptote at y equals 0, my vertical asymptote will exist for my logarithmic, and they flip-flop. But it is very tempting to maybe think that there's a horizontal asymptote for this green inverse logarithmic function. It just grows very slowly. So when I plugged in 4, I only got 2 out. It takes a long time to grow with that. Okay, so that's kind of our first example of without transformations, how they look. Remember, inverse function should fold over the line y equals x. Let's see if I can draw that in there. Okay, so they should fold nicely over the line y equals x. When you're done, domain and range, all ordered pairs will switch. And it is called a one-to-one graph. And again, one-to-one means it will pass, visually speaking, past the horizontal line test, which the blue graph originally 2 to the x does graph and pass the horizontal line test. So it will be one-to-one or invertible with that. Okay, so how do you see how do do you see how logs and exponents are related, and how do you remember their asymptotes? Well, a few years ago, I had a student come up with a saying, and it doesn't quite make too much sense, kind of like the word PEMDAS, but it helped them. And they said logs are cut in Virginia. All right, the good old state of Virginia. And I don't know how many logs are actually cut in Virginia, but they said that. So logarithmic functions have vertical asymptotes. And they said houses are expensive in the Hamptons. Well, I was like, oh, well, where are the Hamptons? The Hamptons are part of New York. They're really, really expensive homes, really, really expensive. So EXP for exponential, and they have HA for Hamptons, horizontal asymptotes. But if you can remember one, then you may not need to remember that houses are expensive in the Hamptons. Just logs are cut in Virginia are going to maybe be a good way to remember logs have vertical asymptotes at x equals 0. You do not have to memorize it this way. It just was helpful for that student, so they shared it with the class. And if you can come up with a better one, by all means, shoot me an email, and I'd be happy to add yours to the list of ways to remember how logs and exponents are related and which one has which type. But the reason why it's helpful to know that logs have vertical asymptotes, again, scrolling back up, is this graph really does take a long time to grow right here, and it does take a while to see that it does keep growing, and it may, unfortunately, visually look like you have horizontal asymptotes for log functions, and you do not. The blue function, the exponential function, can never dip below 0, so the logarithmic function can't ever go beyond 0 for the x values. So they do switch, but it's not both ways. All right, let's go ahead and take a look at our next example. We're going to do one more exponential one with some more transformations. And we're going to be finding its inverse to this number 1 as well. Okay, so let me move this down a little bit. All right, so let's see what we can come up with. So first off, let's start with transformations. I'm going to stay with blue for my exponential functions. Again, if you're graphing with multiple colors, you might want to do that. So this one has a 3 to the x minus 1 plus 2. So that x minus 1 is all up in the exponential position, and it's trapped by the x. You could even put parentheses around it. So this one shifts right 1, and then the next one is a vertical shift up 2. Okay, so those are going to be our two pieces. So if you already know what the graph looks like, you can graph pretty quickly, but we're going to get some smart points with this for this. So one of the things we want to do is get our exponent to equal 0. Well, in order to do that, we would have to be plugging in a 1. So we want to get b to the 0. And so if I plugged in 1, I would get 3 to the 0 plus 2, which will be 1 plus 2, which is 3. So that's a good place to start. So I'm going to go over 1. I'm going to be up at 3. Okay, so go ahead and plot over 1 up 3 right here. Okay, and then you want to pick points in either direction. So like 0, maybe -1, -2, you could keep going, 2, and then 3, and so forth. So I'm going to go ahead and move in the positive direction first. So it's 3 to the x minus 1. So it's 3 to the 2 minus 1 plus 2, which 2 minus 1 is going to be 1. 3 to the first is 3, plus 2 is 5. So at over 2. I'm up at 5. All right here. And then when I plug in 3 to the 3 minus 1 is 3 squared. Plus 2 is going to be 9 plus 2, which is 11. That already is going to shoot off my graph. So right over here, I'm going to kind of there's a point up here. When I plug in 0, I get 3 to the -1 plus 2, which is going to be 2 1/3. Okay, so at 0 over, I'm no longer at that nice smart point of 0, 1. That y-intercept is shifted. I'm going to go 2 1/3. And then when I'm at -1, I'm going to get 3 to the -2 plus 2, which is going to be 1 over 3 squared, or 1/9, plus 2 is 2 1/9. So notice that the 2 stays there, but that fraction, 1/9, is getting tinier. So at -1, I'm at 1/9. And then if just kind of in my head, if I plugged in -2, I would get 3 to the -3, which would be 1/27 plus 2. So it's getting really, really close to that. So you can keep plugging in numbers as needed, and you should end up with a graph like that, okay? Bearing in mind trying to keep the x points. Okay, so that's going to be our exponential function. So we kind of already have gone over how to write the equation of the inverse by switching x and y and solving backwards for y, and we're going to try to graph that. in just a minute. So let's go ahead and get our properties. The domain then of our exponential function, I can plug in anything I want. So all real numbers between negative infinity and infinity. All righty, and then our range, we still have, man, I missed my horizontal asymptote. How did I do that? Oh, because it's up 2, so I apologize. So 2 1/3 is right here, and then 2 1/9 and 2 1/27. So it actually should look more like this as we're growing. So it has a horizontal asymptote of 2. Got to be careful there. I was just kind of plotting away on that. So I'm going to go ahead and graph that in a pink color. We shifted up 2, so y equals 2 is a horizontal asymptote. Okay, glad I caught that. So, and then our range then is going to be 2 to infinity. So if we're shifting up 2 and we have horizontal asymptotes, then the horizontal asymptote will also shift up 2. So again, y equals 2 is going to be our shift up, right? So again, houses are expensive in the Hamptons. If you kind of want to remember that exponential functions, which is what this is, have horizontal asymptotes. So if it's shifted up 2, the vertical shift up 2 is going to affect that graph. Okay. All right. Then let's go ahead and find the inverse. Hopefully that wasn't too bad for you. And we're going to then graph the inverse, which you could graph from this picture if you wanted to. You could go ahead and do that, taking all the ordered pairs and switching them. But I'm going to go ahead and find the equation first. So in order to find the inverse, we're going to switch x and y. So it's going to become x equals 3 to the y minus 1 plus 2. And then we need to solve backwards for y. So be very careful about that. That plus 2 is all the way out on the right side. So I'm going to move that to the left or subtract it from both sides, keeping it equal. And then I have 3 to the y minus 1 left over. Okay, I cannot add the 1 over. It's up in the exponential position. So I need to convert to logarithmic form. Remember, the inverse of an exponential, we're going to need to have log in there. So my base is 3. So this is going to become log base 3 of x minus 2. I'm going to put that in parentheses right away so I don't lose it, equals y minus 1. So when we don't know how to solve for an unknown exponent, we have to convert forms. Now I have that 1. I'm going to add 1 to both sides. But notice that I put parentheses around the x minus 2. I cannot change that. That plus 1 is shifted outside. So it's going to be log base 3 of x minus 2 plus 1. Okay, so this is going to be, instead of shifting, the original function shifted right 1 up 2, this function is shifting right 2 up 1. Okay, so that is going to be our exponential, it's just y, so it's like our y inverse equation is going to be log base 3 of x minus 2, that quantity, plus the whole thing shifted up 1. Okay, so let me get that y inverse a little bit nicer. So that's how that works out. So that's our equation of our inverse function. And then we're going to go ahead and graph it and state the domain range, which are going to flip-flop. Alrighty, so then up here, we're going to have this, and so it's going to have, so the y inverse equals log base 3 of x minus 2 plus 1. So we're going to shift up 1. We could take all the ordered pairs and switch them. So let's see, so the nice one is 1, 3, so this one's going to be now 3, 1. And then 5 over, we're going to be up at 2. So I'm just switching these ordered pairs. Okay. And then at 3 over, we're up at 11. Or sorry, 11 over, excuse me, we're up at 3. So we're growing really, really slowly. And then over here at 2 1/3, so right about here, we're up at 0. So I don't know what that, oh, I didn't mean to put that ordered pair there. And then at, we have 2 1/3, and then I need to shift that over, sorry. What did I plot here? This is over 3, 1, 2, 3 up 1, and then 2 1/3 is at 0, and then we get really, really close to it. So our graph, I'm going to do my best job trying to graph it on this screen here, gets really, really close to a vertical asymptote of 2. So if we have a horizontal asymptote for our exponential function, we're going to have a vertical asymptote. Let's see if I can get it in magenta again, at 2. So vertical lines are a little trickier to graph for me. I'll do my best here. And then that's going to be at x equals 2. Okay, so that's going to be our function. Our green function is going to have the domain, range, and asymptotes right up here are all going to switch for our inverse function and because of the inverse relationship. So the domain is going to be from 2 to infinity. That's that vertical asymptote that I put in that magenta pink color. The range is going to switch to negative infinity to infinity. And then the asymptotes are going to be, instead of y equals 2, it's going to be x equals 2. Our asymptote here is going to be x equals 2. So hopefully that graph, not the best with the digital pen, but still pretty good. We'll fold over the line y equals x, and everything reverses with the inverse function. Okay, some of these smart points here, why do I have like log base b of 1 equals 0? That's because if I have right here my log function, okay, if I can get it to be log base 3 of 1, that has to equal 0, because when we convert, we would get 3 to the 0 equals 1, which is a true statement. And log base 3 of 3, let's say, is going to be, when I convert, that's going to equal 1. That's because the base is 3. 3 to the first has to equal 3. So you can also graph log functions a little bit. They don't have tons of nice ordered pairs, but if you can get this base x minus 2 equal to 1 and then equal to 3, you can have at least 2 smart points for your graph. Okay? All right. Let's go ahead and do one last one where we're doing graphing of a log function in log form and then converting and finding the inverse of that. Okay, so I encourage you to pause the video and go ahead and graph your logarithmic function. I'm going to stay in green and then see what you can come up with on your own. Okay, so hopefully you paused. All right, so this is going to go right 3. Okay, the domain is this position, our anti-logarithmic position, can never be equal to 0. It has to stay greater than 0 or positive. So if I add 3 over to the right, okay, x has to be greater than 3. So actually the domain is pretty quick to find with log functions. That position has to stay positive. So from 3 to infinity is going to be our graph, which also indicates the asymptote. Remember, logs are cut in Virginia, if that helps. We're dealing with a logarithmic function. So we're going to have vertical asymptotes for that. And it's going to be, since our domain is going to be greater than 3, our vertical asymptote is x equals 3. Okay, so just that's sometimes really nice to put in right away, and maybe then even on your graph, go over and say, okay, I have a vertical asymptote at 3, and get that in there right away before you accidentally miss it or misplot a point like I almost did on my last one. Okay, so that's my vertical asymptote for my logarithmic function. All right, and then let's talk about these smart points a little bit. So if I can get it to be log base b of 1, then I can get it to equal 0. So if I want it to have that equal to 1, I can have the x minus 3, I need to equal to 1. So if I add 3, when x equals 2, I get that scenario. So when I have log base 4 of 2 minus 3, oh, sorry, it's 4. When I plug in the 4 minus 3, I get log base 1, log base 4 of 1. So that's going to be like, if you don't know what that equals, you could convert it. So 4 to the x equals 1. Well, then x has to equal 0. Okay, so when I plug in the point 4, I get 0 out. And then the other smart base one is when I can get it to be log base b of b. Okay, so what number can I plug in for x that would cause it to be log base 4 of 4? Well, that should be log base 4 of, let's say if I plugged in 7, I would get that. So when I plug in 7, I get log base 4 of 4, which has to equal 1. Okay, so those are some numbers that help, but also knowing the vertical asymptote. So over 4 up 0. And if the normal logarithmic function crosses at 1, 0, then this has been shifted right 3. So that would hopefully make sense that the ordered pair shifts. And then at over 7, I'm up at only 1. So it's growing very slowly, and it should look something like that. Okay, so that's my function, g of x. And then we're going to go ahead and find its inverse and sketch its inverse. And I didn't put in here its range yet. Its range is all real numbers from -infinity to infinity. I can get out any values I want. It just takes a really, really long time to grow. All right, so we're going to find the inverse of the log base 4 of x minus 3 and graph it on the same axis. So again, I'm going to switch to my blue pen for my exponential functions. I encourage you to pause the video and try finding this inverse on your own and sketching the graph. All right, so my first step is going to switch x and y. So my g of x is really a fancy way of saying y. So it's going to be x equals log base 4 of y minus 3 in parentheses. So I have to start working with this. Well, I'm kind of trapped here, so I need to convert to exponential. Since I'm trying to go from logarithmic form, my inverse is my exponential. So it's going to be 4 to the x, that's my base, 4 to the x equals y minus 3, and then I need to add 3 to both sides. So y equals 4 to the x plus 3, and I'm going to rewrite it with the notation since my function's name is g. G inverse of x equals 4 to the x plus 3. So if the original transformations for my exponential function are right 3, then for my logarithmic function, they're up 3, so both in positive directions. So I'm going to take my exponential function, and you could take the ordered pairs at 4, 0, and 7, 1 for my logarithmic and switch them to 0, 4, and 7, or 1 over up 7. And then it's going to have, since we have a horizontal asymptote, a vertical asymptote of x equals 3, we have a horizontal asymptote of y is going to be equal to 3. Okay, so I'm going to switch my colors one more time, and I'm going to put that in right here. So up 3, we have a horizontal asymptote of y equals 3, and then I'm going to go ahead and sketch my exponential function. So you can get lots more points if you like, but you don't necessarily have to. And it should go something like that. And not my best one, but trying to get it up with that. You'll have my math lab tonight, so it'll look a lot nicer with that. Okay, so that is what is going on with that function. They fold over the line y equals x, and we're converting forms. So just trying to get comfortable with, remember, exponential functions have horizontal asymptotes, and vertical functions have, or logarithmic functions have vertical asymptotes. So it's something to keep in mind. If you want to memorize it, as logs are cut in Virginia. So up here, kind of a little saying, logs are cut in Virginia, logs have vertical asymptotes, houses are expensive in the Hamptons. Again, a student came up with that. Hopefully that helps with you. If not, you can come up with your own saying or phrase. So our log properties then are log base a of x, a has to be greater than 0, a cannot equal 1. The domain is from 0 to infinity. The notation for range is -infinity to infinity. And the x-intercept is 1. There's no y-intercept. So everything switches here. We have a vertical asymptote of 0 for logarithmic functions, and they're increasing very slowly. Logarithmic functions is decreasing when the base is between 0 and 1, but it's increasing when the base is greater than 1 for a. And then contains the points 1, 0, a1, and 1 over a I didn't show, but that does contain it with -1. And the graph should be smooth, continuous, with no corners or gaps. Our last one, I don't want to do too much time with it, but it's just exploring e to the x. Actually, e is defined as a limit as n approaches infinity of 1 plus 1 over n to the n. What does that really mean? It means as n gets really, really large, as n approaches infinity, what happens to those outputs? So I'm just going to pop up the calculator and show you. Here's what e to the x looks like. So e is right here, over here under second divide. So if you hit second and divide, you'll get the e button. So you don't want to use rounded values for that. And e to the x, and then I did zoom 6. Oopsie, zoom 6. And I got my graph. It's going to look like an exponential function. But what is the value of e? Well, we can actually calculate that by putting in very large values of this 1 plus 1 over n to the n. So what I'm going to do is I'm going to go ahead and put that right here. So this is 1 plus 1 over, I'm going to use x raised to the x. And we want to see what happens that gets really, really large. So to do that, I'm going to go to second graph, which is my table feature. I think I'm still under ask. It doesn't look like it. So I'm going to go to second table set under window. And I'm going to change it to ask. We did this a little bit with our rational functions. Okay, and then I'm gonna now, so that's under table set, under just independent, not dependent, and then I'm gonna go to table. So let's say what happens when I plug in 10, and we're actually looking at y sub 2. So I plug in 10, hit enter. Okay, when I plug in 100, hit enter. When I plug in 1,000, and we're gonna see that it's gonna start plateauing towards a number. And what's my next one? 10,000, and then 100,000. Okay, so when I plug those in, this is the number we're approaching, and it's 2.71826 and so on. Well, that is our value for E. Okay, so E is an irrational number that does not repeat or terminate. It's getting closer to 2.718 is what I'm going to put. And if we raise that E, if you have Y equals 2.718, it should make sense that's exponential growth because your base is larger than 1. It looks something like this with that. Okay, the inverse of E, we kind of did at the beginning with that, is the ln of x. Okay, so that's the inverse of E, and if we were to graph that, it would cross at 1 and would have still, asymptotes are going to still switch out. It's going to look something like that. Fold over the line y equals x. So this is the ln of x, and the one in blue is my e to the x function. So they have switching of domain and range. Okay, so that's how those work out. Down here it just says, can we graph the natural log of x plus 2? Well, that's what I have in red up here, but it's been shifted left 2. So this is going to be shifted left 2. So if you can use the parent function and say, well, everything's going to shift left 2, how will that look? The x plus 2 has to stay greater than 0. Okay, so x has to be greater than -2. So that's going to be my vertical asymptote. Okay, so it's going to look something like that. And then, so if we're looking at the graph right above, then all I need to do is shift it left 2, but the x-intercept, everything like that is going to shift as well. So instead of crossing at 1, it's going to shift left 2. It's going to cross at -1. And then the horizontal vertical asymptote is now going to be at x equals -2 is the vertical asymptote. So we have a vertical asymptote because x can never be greater than, x has to stay greater than -2. So we have a vertical asymptote of x is equal to 2. So it'll look something like that. And it grows very slowly, but it does grow to the right. So that's one way to graph natural log. So on your homework tonight, you're going to be asked to graph both. Remember, you're going to have to change the base. Now this one has ln is going to actually be log base e of x plus 2. So you would have to change the base to e. And this one that we did right above here, in this example, we would have log base of 4. So we did do a tutorial of how to change those bases and then type in the horizontal and vertical transformations. Let me get rid of that, sorry, on that. Okay, I hope that helps. Again, please reach out with questions and concerns, and that is graphing of exponential functions and a little bit of E as we move into our properties of logs as we move forward.